Hello, in this lesson, we're going over the midterm exam and review the contents in the past 8 weeks. Well, we have the first question, okay? It's really testing you about using the, know how to use cited limit. And the concept being tested, of course, the definition of limit and direct substitution property, one-sided limits, and the theorem, if limit exists. Here it should be an L. It should be an L. Right, if limit exists, then limit from right and limit from left both exist and they are the same. And so this is what this first question is testing us on. Okay. Now, as we look at the question, right, if you're not familiar with the function and how to graph them, and that should not bother you, because these are trig functions. And some of you are familiar with the curve, some of you may not be super familiar with the curve, and you can graph all three curves in each related interval, or you can just simply mark it as I do here. The first function, which is 1 plus x, this is the definition of function when x is less than 0. So I put it as green. And the one in the middle is cosine x. Okay, that's between 0 to pi, including 0 and pi. And the third one is when x is greater than pi, and I use the color purple. And so you can see the function actually is defined on the entire number line, even though this question was not asked. But you understand this is a piecewise function. The domain is all real numbers. Okay, so the domain is all real numbers. And since it's not asked for, so you don't have to mention this. But I mentioned it here just to, since we talk about this, so I just put it here. Not necessary, it's just for you to understand. The function is a piecewise function. So when you look at it, 0, right? So there's 1, 2, 3, 4 questions about the function's limit from left, right, at 0, and the function's value at 0. So all these 4 are the questions in our consideration. So this is about the limits and one-sided limits, okay? And this is theorem, right? If a limit exists, if and only if, right, limit from left and limit from right both exist and they're the same. Okay, so from left, when we look at the function of where x is approaching 0 from less than 0, so this piece, we know that the function assumes this 1 plus x, right? That's 1 plus x. So we're going to replace f of x by 1 plus x. And then we can use direct substitution, and that's going to be 1 plus sine of 0. Because when x is approaching 0, from smaller than 0, x is less than 0. So if condition is satisfied, sine of 0 is 0. So this value equals to 1. Now, limit from right? When x is larger than 0, then the second function, cosine x, will be applicable here, right? When x is larger than 0. So this interval describe, second function cosine x is applied when x is between 0 and pi inclusive. So here you have cosine x. Direct substitution is cosine 0 equals to 1. Okay, limit from right and limit from left both exist and they're the same. So now you're applying this theorem. So the limit equals to one of it, equals to the same limit, right? You can quote definite, you can You can quote the definition if you wish, right? You can quote the theorem if you want, right? But its context is pretty obvious. The context is pretty obvious, right? If you like, you can write it down as because, right? Limit from left is the same as the limit from right. And that is the same, which is 1. F of 0, right? F of 0 when x is equal to 0. And that's when the second function is going to be used, because you look at the interval, right? When x is greater than or equal to 0. So this equals to cosine 0. Cosine 0, of course, equals 1. In this case, actually, it's continuous, but we didn't ask that question. Okay, we didn't ask about it. Okay, so the second one, the second group is about in the neighborhood of pi, right here. In the neighborhood of pi, the same concepts are being examined, right? I examined whether you understand how to use the notation. So before pi and after pi, so we have the function here, right? I can bring the picture down, right? I can bring the picture over here, right? So for our convenience, so before and after pi, right? When pi is approached from smaller than pi, that's we're taking limits of f from the left of pi, and that cosine function applies, direct substitution, cosine pi. Cosine pi is equal to -1, okay? When x is approaching pi from larger than pi, and we're approaching pi from larger than pi, so the purple function is used, the sine x. Direct substitution, sine of pi is 0. And in this case, this limit, right? According to the theorem, the limit from left and the limit from right are not the same. Therefore, we say the limit does not exist. Because, you can tell the reader, because the limit from the left is not equal to the limit from the right. They both exist, but they're not the same. They're not the same. You can use DNE if you wish. And f of pi at pi, okay? We use the rule for cosine. So cosine pi, and that equals to -1. So these are basically, we're testing you these very basic concepts. Okay, the second question is about continuity. Okay, so we want you to explain why the function is discontinuous. At a equal to 0, at the point equals to 0, right? Once again, if you look at the function, we use the same strategy, right? You don't have to know these functions graph, as long as you know the function somewhat, right? And when x is less than 0, we have the green. At 0 is red. There's only 1 point. When x equals to 0, for larger than 0 is 1 minus x squared, the purple. Okay, so to demonstrate, to demonstrate the function is continuous, of course, we're working with the continuous function definition. So we're looking for the definition of continuity. Here, I think I should have the L here. Okay. we'll come back to the, here, continuous function. Okay, continuous function. Continuous function is, we know it has three elements. First, it has to be defined at the point, right? If it is not defined at the point of consideration, then it is not continuous. So we check the condition one by one, and we start with the easiest. Right? And the first condition, and we can see obviously f of 0 is 0. It's defined, right? Second one, we're going to check if the limit for the function exists from left or right, right? So the first condition, second condition, right? Second condition, we're going to find the limit. So we're going to look at the limit of the function as x approaching 0, because there's three pieces, right? X is approaching 0. From smaller than 0, we have different rules of the function. Therefore, we have to use a one-sided limit. And we also have to consider the limit of the function when x is approaching 0 from larger than 0, right? So you can see why we use this, because we have piecewise functions in our discussion. So we look at limit from left, we look at limit from right? On the left is cosine x. So on this piece, limit as x approaching 0, from smaller than 0. And the rule of the function is cosine x. Direct substitution, cosine 0 equals to 1. And the next step, right, we take the limit from right. And the rule is 1 minus x squared. 1 minus x squared, this is a quadratic function, this is a polynomial, direct substitution works, so we're going to do a 1 minus 0 squared, right? Limit exists, right? Limit from left and limit from the right are the same. So the limit of the function exists. The second condition is also satisfied. So when x is approaching 0, you see we're working on this piece, right? The limit exists. And we also relate to what we just talked about, the limit from left and limit from right. The one-sided limit. The one-sided limit. So we're using this piece, this theorem, to find a one-sided limit. And both sides of the limit, they're equal. So this limit when x is approaching 0 is 1 because of this theorem. You see, the theorem is very, very useful, very, very powerful. And it's often, and I frequently test it, right? And you don't have to quote the reason now because it's pretty obvious. It's pretty obvious, right? So you can conclude that. You can say thus, right? Consequentially, right? And now then we go back to the definition of continuity, right? The limit exists, but it is not the same as the function's value. So this limit, although it exists, does not equal to the function's value at 0. You see in this last expression, you can write it in many ways. You can write a 1 is not equal to 0. But I think really the best way is quoting the definition. The best way is really quoting the definition, right? When x is approaching 0, f of x, the limit does not equal to f of 0, right? We talk about how, we apply definitions, theorems, and we quote the theorems and we quote the definitions, and oftentimes these turn out to be very powerful. Then you say, therefore, Therefore, the function f of x is not continuous at 0. Okay, you have to indicate where it is not continuous, where it is discontinuous. Okay, because everywhere else, this function is continuous. Okay, so you say f is not continuous, then that sentence is incomplete. And if you have incomplete sentence like that, it will be taken as saying the function is not continuous everywhere, somewhere, where. So you have to express it concisely. We want to express it concisely. Okay, so question number 3, we apply squeeze theorem. Squeeze theorem, okay? Squeeze theorem, and of course we've learned squeeze theorem. So I'm gonna bring you the squeeze theorem. Wait. Oh, did I delete that? Oh, question number 3, right? I'm sorry, this apply squeeze theorem to prove that the limit as x approaching infinity and here we have sine square of x over 1 plus x squared equals to 0. You know, the version of squeeze theorem we learned are here. Okay, so look at the squeeze theorem here. So this squeeze theorem, certainly it would also apply if x is approaching infinity. Okay, so we're using the other version of it. Okay, so so if I'm going to make a new slide, okay, just copy this, right? Just copy this. Wait, copy this and paste it here, right? Remove that. The squeeze theorem. The squeeze theorem. There are two versions. So if this is approaching infinity, right? If this is approaching infinity, so let me make that change, right? If A approaches infinity, it will also work. Okay, it will also work. So let me put insert equation, and I'm going to put it here, infinity, right? So here, infinity, right? So it's just squeeze theorem you can use, you know, we really just use the idea. And I thought it would be fun to, you know, to have this version tested on. And besides, this is one of the homework questions. All right, there are more than one way to prove this. So I'm going to prove it, you know, using this relatively simple version of it. Some of you used like sine x is between -1 and 1. You can certainly use that for sure. Okay, but because here we have sine square of x, right? So we also know this version of it. You can use this version of it. You know, sine, the absolute value of sine x is less than equals to 1 for any real number, for any real number. Of course, the setting we're considering is x is approaching infinity. When x is approaching infinity, I really want to bring this up, bring the definition. Okay, bring up the definition. What does it say? Right, you look at the definition, you intuit the definition of limit at infinity. So when x is approaching infinity, okay, let me make this a bit larger. Okay, when x is approaching infinity, then we say the function is defined on interval from a to infinity. So we can assume this a is sufficiently large, so large that on this interval, this x is very large, so x squared is very large, right? So we can obviously see this is, of course, is going to be true, but we have to get there from the, the known facts, and sine x, absolute value of sine x less than equals 1. This is true for anything. So you can either use this one, but I'm going to use this piece. Okay, you're going to see how simple it is. You can use either one. So this is always true for any real number x. And of course, this is true for, any interval you name it, right? And when we square both sides, both sides, we basically get sine square x this is going to be less than equals to 1. At the same time, it's going to be greater than equals to 0. Because anything squared is going to be at least 0, right? In fact, you could start from here. Just, past this one, because we know that's a fact, right? Once we have this set up, sine squared of x between 0 and 1, which is always true for any real number, right? Let's just write it down for any real number. For any real number x. Okay, this symbol means for any real number x. Okay, for any real number x. And then you can multiply 1 over, or divide every side by 1 plus x squared, because x squared is going to be at least 0. 1 plus x squared is always going to be positive. So on all these sides, you divide by 1 plus x squared. Okay, you divide every term by the same quantity, which is a positive. In fact, we're using the property before squeeze theorem, this piece. We're actually using this theorem here. Okay, we kind of take it for granted that this is true. Okay, we kind of take it for granted this is true because we're going to use it right away. We're going to use it in a minute. Okay. So we have this situation that is between 0 and 1 over x squared. So now this step is actually optional to show. This step is optional to show. You can just show the next step directly because 0 divided by a positive number is 0. A limit of 0 or x approaching infinity is 0. Okay, so then you take the limit, right? You take the limit of 1 over x squared, and that limit is 0. Okay, and the limit of 0 is 0. Then you can say by squeeze theorem, and that limit is squeezed in between is 0. Okay, so that's proved. And some of you prove it other way, that's okay. But I really find this way is actually much simpler. Okay. All right, number 4. Piecewise function again. Okay, piecewise function again. And here, in this question, we have we have some questions. We really want to touch you guys on the concept of continuity, continues from left to continues from right, right? So we're going to bring up the flashcards, right? Definition of continuous from left, continuous from right, right? This sort of thing. Okay. So we're testing you on these concepts. Okay. So we say f is given as follows. First, give the domain. Okay. Give the domain. The domain. If you draw a chart like this, you can see less than 0 is covered. Between 0 and 1 is covered. Larger than 1 is covered. Right? So the function, the domain of this function is from negative infinities to positive infinities. All real numbers. Okay, every number is defined. Every number is defined. Question B. Question B is about find the numbers at which f is discontinuous. Okay. Well, if you look at these intervals, the only 2 points that may be suspicious is the point 0, which is where the 2 pieces of functions are used, right? The 2 pieces. So in between, right, for x less than 0, when x is less than 0 is continuous because we have theorem about continuous function. See, we have any polynomial is continuous in its domain. Now for x less than 0, it is continuous. And this theorem says, the polynomial is continuous, 2 minus x is polynomial, x plus 2 is polynomial, they're all continuous. So they're certainly continuous in their specific, smaller interval between 0 and 1, right? E to the power x is continuous in its domain. It's certainly continuous between 0 and 1, except that at the point 0 and point 1, we have to give some special consideration. Okay, so first you may like to make the statement, but if you don't, because the question is asking where the function is discontinuous, right? But I hear as I'm talking about this function, okay, f is continuous. Oops, is continuous. Okay. For x less than 0. Okay. And the other one is or between 0 and 1. Okay. Or x is larger than 1, which is guaranteed by theorem. Guaranteed by this theorem. Okay, guaranteed by this theorem. Only 0 and 1 are questionable. Only 0 and 1 are questionable. So we're going to look at 0 and 1, and we have to look at this one-sided limit, right? We have to look at, so this time we are going to create. So we're going to study, right? We're going to observe continuity at a equals to 0, right? And of course, the next we're going to observe continuity at 1, right? So these are the only 2 places we have to consider. Of course, this question is asking, right? So these 2 points are suspicious, so we're going to work on them. So I drew this graph as was before, right? So we observe, well, the function is defined everywhere, right? So f of 1 is defined, right? You can see f of 1 is, f of 0 is defined. F of 0 is e to the power 0, right? E to the power 0 equals 1. The first question, right? The continuity definition. Where's the continuity definition? Right here. So A, B, we're going to look at limit. We're going to look at limit, right? The limit when x is approaching 0 from smaller than 0, right? F of x. And we're going to just, the second one, we're looking at the limit, right? And we're going to consider limit of f of x when x is approaching 0. X approaching 0 from larger than 0. Okay, and we look at f of x. So we look at these two, and then of course C, we're going to observe it are the same. But there's also there could also be some flexibilities here. Okay, let's take a look. Let's take a look. Limit from left when x is approaching 0, and x is approaching 0, x is negative. So we're going to use the rule x plus 1. So limit as x approaching 0 from smaller than 0. So, okay, we use the rule of x plus 1, x plus 2. Direct substitution, what do we get? We get 0 plus 2 equals to 2. Now, what do we see? Okay, you could find the limit from the left, and you also find the limit from right. Okay, and I'm going to show you there's some flexibilities here. So here, if I keep the same track, okay, and when x approaching 0 from larger than 0, that's going to be e to the power x, right? And that's direct substitution, e to the power 0, and that equals to 1. And you can say, oh, the limit from left and limit right from right are not the same. In fact, because we have so much evidences, so much evidence that we can actually quote, right? This limit, the limit from right or the limit from left is not the same as the function value at the point. Okay, so I'm going to give you multiple versions. The first version, of course, you can say the limit does not exist. The first version, it was pretty straightforward. You can limit as x approaching 0. I'm going to show you a case by case. Okay, f of x, okay, does not exist. Does not exist. And do we have to check C? No, we don't need to check C anymore. Okay, because the second condition. So C is not necessary to check, so we remove it. So by this time, we can say F is discontinuous at 0. Okay, here I'm going to put a note. There could be another version. Okay, there could be another version. Another version to say f is discontinuous at 0, you can also say, okay, you can also say this limit, the limit from the right, from the left, is not the same as the function's value at 0. this is also a violation of continuity, right? Because this limit implies, the third condition implies the limit from left is the same as f of a. The limit from right is also the same as f of a. Okay, so now if this is true, if you point this out, you can also say f of x is discontinuous at a. That is, if you point this out. If you point this out, right, you would not need, you will only need this piece. You would only need this piece. You would not need to do these work. Okay? The other way to demonstrate this continuity, you can do that. You can do that. Okay? It's just a note, right? So you understand there's a variety of ways to doing it. Now, so 0 is a point of discontinuity. How about 0.1? Right? How about 0.1? At 0.1, we pretty much do the same thing, but you understand the flexibility. You understand the flexibility. Okay, so we reserve the limit at 1 for our convenience. I'm going to bring this picture to over here. Right, so now we're looking at 0.1, and we're going to look at the, the limit of the function. Of course, first of all, is the function defined f of ABC, right? ABC. So A, B, right? So f of 1. What is f of 1? F of 1 is e to the power of 1. E to the power of 1. E to the power of 1 is e. B. We're going to look at limit from left to right, right? Limit when x is approaching 1 from smaller than 1, if you wish. Smaller than 1, and f of x, and that should be the limit of the function of choice when x is less than 1. It's e to the power x. So this piece is e to the power x. Okay, direct substitution is e to the power 1. And that equals to e. Right? Well, these two are the same. You have to continue to look. So what if x is approaching 1 from larger than 1? So this is a plus sign. Right? So in that case, when x is approaching 1 from larger than 1, it's 2 minus x is the rule. 2 minus x is the rule. So 2 minus x. Direct substitution, what is it? Direct substitution is 2 minus 1 equals to 1. So now we are in a situation that the limit does not exist. Okay, so the limit does not exist. Then you would say the limit as x approaching 1, f of x does not exist. Do we need to check further? No need to check further. Okay, second condition is not satisfied. Then you can say f is discontinuous. F is discontinuous and 1. Okay, once again, I put a note here. You can also point it out. Okay, you can also point out that if you just do this piece of work, right? No, wait. You can point out the limit from right of 1, okay, is not the same as this piece. Okay, they're not the same. You can also declare that continuity. Okay, you can also declare the discontinuity, in which case you only need this much work. You see, you can do these and decide which one, which piece of work is necessary. You don't have to give like 10 reasons, even one reason will be sufficient, right? And of course, you find the limit from right of 1, and the limit from right is not the same as the function at the point of 1. So once again, that's another way to say, that's another way to express, to demonstrate discontinuity. We do have flexibility. Here. If you understand these concepts very thoroughly. Okay, it's very good practice. So by this time, we have answered the question of B, right? And in summary, you can say f of x, okay, is discontinuous at a equals to 0 and a equals to 1. Well, you can just say 0, 1. Okay, now question C. Find the numbers at which, okay, at which of these numbers in B, we have 2 numbers. F is continuous from right and F is continuous from left. Or neither. Okay, see. So I'm gonna copy the question. Okay. Okay. Let me just copy. At which of these points in B, F is continuous. F is continuous from right, from left, or neither. So this would require us to follow this definition. Okay. We actually could see what from the work we did. We just have to put the definition really. Okay. 0, 1 are the 2 points we have identified. They are just continuity points. Okay, they are the points of discontinuity. So at 0, right? At 0, what have we found? At 0, the limit from right equals to 1, right? So we're going to bring these 2 together. Okay. You wouldn't need these. Oops. You wouldn't need that. You just basically point out that the obvious work you've done, right? So the limit from right, the limit from right is the same as the function's value at the point. So then what you say is that F is continuous is continuous at 0 from right. Is it continuous from left? No, it's not. Okay, because we just did, it's 2, right? That's not the same, right? The limit from left is not equals to 1, right? So at point 1, what have we found? We found that the limit, so at point 1, the limit at 1, these two are the same, not the other one. So we got A, right? F of 1 equals to E, the limit for x is approaching 1 from smaller than 1 is also equals to E. So we have the limit of this function when we approach 1 from the left is the same as f of 1. We're quoting the definition. We're really just quoting these definitions to draw the conclusion. Then you say f is continuous at, right? Then you say f is continuous at 1 from what? From the left. Okay, so these are the, so this is one piece, right? This is the why, the work we've done, we quoted. And then we quote the definition. And the second piece is that we just take the work we've done, right? Quote the definition and draw the conclusion that f is continuous at 0 from right, continuous at 1 from left. Okay, just by definition, So next we're going to look at these limits. I have copied these questions. Yeah, let's do it. The first one here, we really wants to see if you can apply the definition of limit properly. Okay, so here's the definition of intuitive definition of limit. Okay, we have as x approaching 3, right? As x approaching 3, by definition, x is approaching 3, but x cannot be 3. So x is approaching 3 infinitely close. So we factor the top. And we got it. Because x approaching 3 not equals to 3, so x minus 3 is not 0. We can use principle number 1, and we reduce x minus 3 from the expression. So we're left with x minus 2. And that we can do direct substitution so that 3 minus 2 equals 1. So that's the first limit. The second one, okay, when h is approaching 0, but h is not 0. Okay, so we're going to do some algebraic work. We're going to find common denominator, and that common denominator would be, should I make the fonts a bit larger? Yeah, let me make the fonts a bit larger. Okay, the common denominator is x squared multiply x plus h squared. So we multiply by 1, principle number 1. Okay, and then the numerator times numerator, denominator times denominator. Whoops. Wait. Okay, denominator times denominator, numerator times numerator. So there's a distribution here. Okay. And simplify. This step is actually optional if you've done the work in the, x plus h squared reduced with 1 over x, plus h squared. X squared multiply 1 over x squared, that equals to 1. So that's the next step. All right, this step can be omitted. Okay. And the next one, we're going to multiply this out. Okay, so x plus h squared, and that will be equals to x squared, right? Plus 2 times xh plus h squared. And next, opened up the bracket. When we open up the bracket, the negative sign is distributed to each term inside the bracket. So we get a negative here, and we got a negative here. Okay, so be careful. And x squared minus x squared makes 0. And h can be factored. Okay, h can be factored, or you can factor out the negative h. Okay, let's see how I'm going to factor out negative h. So negative h is taken out, and there's just 1 h left. So this is going to be plus h. And this h and the next h reduced. H is not 0. X, h is approaching 0, but h is not 0. So these two h, you see, we're constantly using these definitions. Okay, so because the definition of limit give us the setting about h, right? So this h and that h is reduced. Now we can do direct substitution, because previously we always have this 0 divided by 0 situation, right? So now we no longer have that situation. So we can directly substitute h by 0, and without having to worry about we're going to get 0 denominators. So h is substituted by 0, 0. And in the end, we have a negative 2x over x raised to the power 4. Right? Because x plus 0 squared is x to the power 2. So we get negative 2x over x raised to the power 4. So in the end, we get negative 2 over x raised to the power 3. Okay. So that's the second question on how to find limits. And this piece is a one-sided limit. Okay. It's on one-sided limit. When x is approaching 0 from larger than 0. Okay. That means this limit setting telling us that it's telling us, right? One-sided limit, right? It's telling us x is positive. The absolute value of a positive number is the same as the number, right? If x is positive. We know that. And therefore, this piece is replaced by x, because when x is positive, that's true. And then what? Well, in the setting, 1 over x minus 1 over x is 0. So the limit is 0. Okay. All right. Number 4. Limit at negative infinity. Okay, limit at a negative infinity. So I'm scrolling down the limit at negative infinity. We have definition, right? When x is approaching positive infinity, when x is approaching negative infinity, right? So this is the definition of x approaching positive infinity, negative infinity. They are similar in a way, right? So for negative infinity, is going to be x approaching negative infinity. So we have those definitions. But the question we have here is that we have a square root and we have x raised to the power 3. So when x is approaching negative infinity, we can assume x is going to be in the interval, right? So we can choose x to be so negatively large, okay? So by definition, we can assume, okay, x is in an interval from negative infinity to a, and a is negative. A is negative because x is approaching negative infinity. And this merely tells us that x is negative. X is negative. If x is negative, right? And from the following technique, I think we talk about similar questions in class, so you know what I meant. So I'm going to come back to fill up the blank here, okay? So you would divide top and bottom by the same quantity, okay, which is x raised to the power 3. So this piece divided by x raised to the power 3. And this piece is divided by x raised to the power 3. And we take x raised to the power 3 and divide. So, okay, hold on. This is minus. Remove that. And the top is divided by x raised to the power 3. Okay, because that's what we're going to do. Okay. We cannot apply any one of the properties of limit because those individual limit does not exist. After this division, of course, you can show this as 1, right? And 2 over x raised to the power 3. So we have a situation like that. So we have x raised to the power 3. We want to bring this x raised to the power 3 inside the square root. But how do we do that? Because x raised to the power x is negative, x raised to the power 3 is negative, right? And the square root of x raised to the power 3, this negative number in the context being squared, right, is equals to, because x raised to the power 3 is negative, it is equals to negative x raised to the power 3. Okay, so recall, I'm certain you guys get this, but I just want to make sure. Okay, x squared equals to the absolute value of x. Okay, the square root of x squared is equals to like that, right? The absolute value of x, if x is positive or 0, oops. If x is greater than or equal to 0, and the absolute value of x is the same as x, if x is negative, the absolute value of x is its opposite. And so so let's not use x, right? Let me use omega. other symbols so we don't get confused, right? So we don't get confused. The same idea. Okay, now x raised to the power 3 is negative. So the root of, right? So that's how we get this. Then from it, right? From it, x raised to the power 3, if we bring the negative sign to the other side, that's negative of that. Does that make sense? I hope. Okay, that equals to this piece. And inside the square root, then you have x raised to the power 6. Okay, I feel that if you have any questions, please let me know, because I might have made this too long, too complicated. Okay. That's really how we get it. So x raised to the power 3, when we want to bring this x raised to the power 3 inside the root, so what we end up with is that we're going to end up with something like this. Okay, so it's going to be root. It's going to be replacing x raised to the power 3, right? So you have a negative sign, so now you can bring them under the same square root. So let me show you. So this negative sign is going to be put in the front of it, and the square root of on top and square root on the bottom, we can bring them under the same roof. Bring them under the same roof. Well, the same square root. Okay, you can see from this step to the next step. So that's how you get this extra negative sign. And of course, the next step is inside the square root. You're going to take square root x raised to the power 6, divide into 1. And you take this piece, divide into 4x to the power 6. So this piece is really just 4. So you have a 4 here. Now each individual limit exists. So what are the individual limits? This has individual limit. This limit exists when x approaching negative infinity is approaching 0. The limit for 4 is the same as 4. When x is approaching negative infinity, this individual limit exists. So now we're applying the properties of limits. Okay. I think I have organized these. Yeah, the limit right here. Okay. Individual limits. When x approaching infinity, that's your limit laws. And to make your work, to make sure the reader understand that you are going through these, you're using limit law properly, then you take this limit, right? You apply to this piece, and you apply to 4, right? You apply limit law, and you also apply another piece. Wait. When you have a continuous function, right? When you have a continuous function, which is this one, you bring the limit across the continuous function, okay? And take the limit over here. I could have put it in front of 4 and 1, but it's not necessary because they're constant, right? By limit law, you see, by limit law, the limit of constant is the same as the constant. So usually we just save that step. We save those extra, right? So by this time, what do we get? This piece of limit is 0, and that piece of limit is 0. So we're going to get square root of 4 on the top with a negative sign on top and bottom. So the limit is 2, positive 2. Okay. Now, last one, limit finding. This limit finding, okay, we have seen, of course, varieties of mistakes. Excuse me. Okay. First of all, we cannot take the limit individually because as x approaching infinity, the limit of ln 2 plus x approaches infinity, and limit of ln 1 plus x also approaches infinity. So infinity minus the infinity, we don't know. So you cannot take limit to the inside. No. So what can you do? Well, we're just going to do some algebraic manipulation. ln, this is applying quotient rule. Okay, so 2 plus x divided by 1 plus x. Quotient rule of logarithm. Okay, ln a divided by b. A is positive, b is positive, is ln a minus ln b. Okay, so we're applying quotient rule from right to left. Okay, from right to left. Okay, left to right. Quotient rule. And then what do we do? Because x is approaching infinity, by the definition, we can imagine x is sufficiently large. How large? As large as possible. It's a positive number. Okay, it's a positive number. And because of that, we can do the following within the logarithm. Okay, and we're going to divide this by x, divide this by x, divide this by x, divide this by x. We're applying principle number 1. The next step, of course, 1, x over x is 1, x over x is 1. Now, we're going to apply this property, this theorem. Okay, f is a continuous, right? The individual has a limit, right? Each individual has a limit. And ln x is a continuous function. So we're applying this theorem, theorem number 8, in a continuous function setting. And by this time, okay, we are going to apply limit individually. Inside. We didn't do it for 1 because the limit of 1 is the same as 1, right? The limit law. So we're applying this property because ln is a continuous function, which is a f outside, and g has a limit. Because the individual has a limit, we can apply the limit. All the limit law applies here. By this time, what do we get? X approaching infinity, so this is 0, and that limit is 0. So we ended up with ln 1. ln 1 is 0. Okay, so that's it. All right. The next one is prove that the equation has at least one root. Apply the intermediate value theorem. Intermediate value theorem, right? We promised you that's going to be tested. So here it comes. Okay, and we use a corollary. So we need to create, in this case, we need to create an interval because the interval is not given. The interval is not given. But how do we create such an interval, right? We have to create a function, I have to create an interval, okay? So I'm going to put some think out loud. The solution, the created interval is not unique. The created function, the new function doesn't have to be unique. But when I think out loud, I'm going to create a function, right? So we talk about that. If this is true, right? And then cosine x, in any order you want, cosine x minus x raised to the power 3 is 0, right? So when we create that function we're going to create is going to be cosine x minus x raised to the power 3. We talk about the difference, right? This is derived from the if statement. When you create a function, there's not an if statement. So you create this function. So don't attach a 0, okay? This just to give you a clue as to how you create that function. So you make a 0 from the equation, so that will give you the clue as how to create the function. The second one is that we're going to create an interval. And that interval at the endpoints, A, B, the function is going to have values that are opposite to each other. So if one is positive, the other one is negative. So it's helpful to know that a cosine, okay, cosine is always between +1 and -1 for any real number, x, right? And so that will give us some idea. So you can try something out. You can try something out. So for example, you can try f of 0, cosine 0, and 0. And that's going to give you cosine 0 minus 0. Cosine 0 is 1, right? And how about, then you have a positive number, right? So you have an interval, you have a positive number. So can we create a negative number? Okay, you think of some of those special values, right? So how about pi over 2? Try it. Okay, cos f of pi over 2, sine pi over 2 over here, x replaced by pi over 2. Cosine pi over 2 is 0. 0 minus this piece, the whole thing is going to be negative. Well, here, you don't have to choose pi over 2. You could have chosen pi. Okay, that will work too. Okay, but the bottom line is that this piece is a negative. This piece is a positive number times a negative number. So we already found the interval. Okay, so we found the point and we found the interval. And what do we do next? All these are things you probably put on your scratch paper, but when you actually show the word, okay, and I'll give you the adequate language to show word. Okay, so you see, when in your proof, right, all these scratch paper thing, we don't need to see. And of course, you can take some of it, right? You can say, hey, let f of x to be this piece. Okay, and then you're going to quote the theorem. You're going to tell the reader f is continuous. Continuous on what? You have to indicate it's continuous on a closed interval, because otherwise the intermediate value theorem does not apply. So f is continuous on a closed interval. You don't have to write the word close, right? As we talked about it before, right? You just have to indicate that. Number 2, you're going to tell the reader that f of 0 is the positive, f of pi over 2 is a positive. You can create your own interval. Okay, the interval I created here is not unique. Okay, so you're basically quoting the theorem right? And do you need to mention f of a times f of b is less than 0? You don't have to. You don't have to because you already have it. You already have it. But if you put it there, that's fine. It doesn't hurt. Okay, and then you say according to intermediate value theorem, there exists a C. Where is C? C is going to be inside the interval. Okay, such that f of C equals to 0. F of C equals to 0. Okay, there exists because the question on the exam said there's at least one. There's at least one, right? Well, there's one. Once you can prove there's one, you have proved there's at least one. Okay. Okay. All right. Such that. Okay. If you elaborate it, because you want to write the final form similar to what is given. F of C, what is F of C? F of C, so we know that the C exists, and that equals to 0. And you can also say there is at least one root C. Okay. If you like, by this time you already finished. Okay. For the equation for cosine x equals to x raised to power 3, you have illustrated that. So that's sufficient. Okay, so that's how you prove it. When you prove it, you just have to quote the theorem. That's what the intention of this question is. And you know how to quote the theorem. You need to mention the function you created is continuous on a closed interval. Okay, if you say an interval that's other than a closed one, then the theorem may or may not apply. Okay, so now let's look at question 7. Piecewise function again, but this time determine whether f is differentiable at 0. Okay, is a function differentiable at 0? How to determine if a function is differentiable or not? By definition. By definition, right? So what's the definition of differentiability? Well, what is the definition of differentiability? Right here. The derivative of function at the number a, denoted by this, is if the limit exists. Okay, so that's differentiability. Okay, we have two versions of the, version, so we're going to use the popular one. And in this case, of course, we're going to consider the limit, okay, as h approaching 0 and f of 0 plus h minus f of 0, because the considered function at the considered point is a equals 0, right? So in the definition, a will be replaced by 0. H is approaching 0, but h is not 0, right? So since it's 0 plus h, 0 plus h is h. So we ended up with a simpler version of something like that. And the rest is just plugging in, right? What? So here we're actually using the definition of a limit. Let's go back. The definition of a limit. Right here. We're using the definition of limit. Does this limit exist? Right? That's our question. Does this limit exist? We don't know until we find out. So what do we have? We're going to plug in. Okay, so maybe I'll make it fonts a bit larger. Okay, as you can see, the function is defined everywhere, but 0 differently. Okay, everywhere else is defined as x squared times sine of 1 over x. At 0, f of 0 is 0, right? So we're going to plug in. F of 0 is 0. F of h, that's going to be h squared, right? That's going to be h squared sine of 1 over h. So we're examining this limit. And on this limit, as you can see, h, well, this is already 0, minus 0. And this, because h is approaching 0, but h is not 0, right? Recall the definition of limit. But so this h and the h from the top can be, we can reduce 1 from the top, right? So in the end, the bottom, the denominator is 1, so we're just left with taking limit of this piece. Now the question is, what is the limit when h is approaching 0? Right? What do we do? Well, at this point, you could be thinking of squeeze theorem, isn't it? Right? This piece, right? If you take the absolute value, right, is less than equals to absolute value of h multiply the absolute value of sine of 1 over h. There. And the absolute value sine of 1 over h, that's always less than equals to 1. So this is going to be less than equals to h. So what we see here is that this piece, right? This piece, i.e., right, is less than equals to h after we take an absolute value. That is, okay, but more algebraic manipulation. So this function of h is between negative of absolute value of h and less than equals to the absolute value of h. It's a squeezy between. But the limit as h approaching 0, right? The absolute value of h is 0, right? So by squeeze theorem, the limit of this piece, right, as h approaching 0 is 0. And now in summary, that means this limit exists. Right? This limit exists. Therefore, right, this limit not only exists, it is zero. By definition of the derivative differentiability, right? Right here, right? By definition, f is differentiable at zero. It is differentiable. It is differentiable. Okay. That's number 8. That's number 7. Sorry, number 7. Number 8. Number 8. Okay. Find an equation of the tangent line to the curve at this point. Right? And of course we know the curve. You can plot the curve, but you don't really need to because I didn't allow you to use a calculator. So you just have to understand the meaning, right? Understand the meaning, right? You understand we need to find the slope of the tangent line. And in order to find the slope of the tangent line, then we know that a equals to 2, right? In this case. So the derivative of the function, at 2 is the slope of the tangent line passing the point. Okay. So now we're going to find f of the derivative of f at 2, right? So we're going to set up the limit as h approaching 0, and the limit of f of 2 plus h minus f of 2 over h. Definition. We use definition. F of 2, of course, is 3, right? F of 2 is 3 because that point is already given. F of 2, if you plug in, you're gonna get 3 for sure. Okay. What is f of 2 plus h? Just plug in, right? Plug in. So f of 2 plus h equals to this piece, right? That's for x. So now x is replaced by 2 plus h. Then x is replaced by 2 plus h. So these replaced by 2 plus h. That's all, right? So f of 2 is 3. So I'm going to put these on the top. So now plug in. Operation f of 2 plus h, that's the piece. F of 2 is 3, right? You will simplify all of these, right? How do we simplify all of these? You can do this on the scratch paper. Okay. So we bring the numerator. So this is the algebraic part, right? 2 plus h to the power 3. And you can do 2 plus h to the power 2 times 2 plus h. And you just do it directly. Just FOIL it. Okay. Just FOIL that. Okay, do these. I'm gonna try to make it shorter because this is gonna be more than 1 hour. Okay, so you do the square and you do the FOIL. So, but anyway, you can just expand it, right? And you bring this expanded form and you bring it here. That is 2 plus h to the power 3 and minus 6 minus 3h, right? Because 3 times negative 3 times 2, that's negative 6. Negative 3 times h is minus 3h. Then plus 1 minus 3, that's like minus 2. And you simplify. So this is a positive 2 and this is minus 2. So now you're getting, what are we getting? These will be gone. Okay. And you factored out the h. You factor out the h. So you have h squared plus 6h plus 12 minus 3. Oh, wait. You know what? This is a 9h, right? Excuse me. This plus 9. Okay. Am I doing well? Looks like it. When it's too long, I tend to make mistakes. So we just going to bring this back in. The denominator is h and the numerator, we have this piece. H and h reduced, right? So h and h is reduced, so we're going to end up with something like this piece. And substitution, direct substitution, so we end up with 9. Okay. So that's how you can manage that. So the slope is found, right? You can tell the reader the derivative of the function at 2 is a 9. And then we can use this, you know, the line, the tangent line, right? Tangent line. So that's going to be y minus 3. The point is 2 comma 3, right? So y minus 3 equals to the slope is 9 multiply x minus 2. Simplify, you get y equals to 9x minus 18 plus 3. That's going to be plus minus 15. That's the line equation. That's the equation of the tangent line. Yes. Now, number 9, true false. True false, these true false questions are really about if you understand these relationships. Okay, so I'm going to show you what these things are. Okay, and we have one more to go, which is number 10. Okay, so let's look at number 9. Number 9, if the limit exists, then f is continuous. Is that true? Let me make this wider. Okay. Well, then you have to compare the definition of limit and definition of continuity. What's the definition of continuous function? Wait, you go through your flashcards. Continuous function. One of the conditions in continuous function, it has to be, the limit has to exist. But there are 2 additional conditions. So simply by limit exists, it doesn't guarantee continuity. So the first one is false. Okay, you compare definition. You compare definition. Okay, compare with box this there. Second, If f is not continuous at A, then f is not differentiable at A. This one is something we talk about in class. If it is differentiable, it is continuous. It should be the last flashcard in your collection this time. If f is differentiable at A, then f is continuous. If f is differentiable, then f is continuous. Okay, so from A to B, then not B, not A. Right? If it's not continuous, definitively it's not differentiable. Okay, so the second one is testing you on that. So the second question is a false. True, false is false. The third one, if f is differentiable at A, then f is continuous at A. That's confirmed. That is true. Okay, so this is true, not false. So the third question is asking directly on the theorem. If it's differentiable, then it's continuous, right? Number 4, if f is continuous, then the limit exists. So we go back to the definition of continuity. Continuity implies 3 conditions, right? And limit exists is one of it. So continuity guarantees that the limit exists at the same point, at this point. And since differentiability guarantee continuity, continuity guarantee limit exists, therefore the last one also is true. So that's about the true false. Okay. Last but not least, we're applying definition as how to find limit right here, finding derivative of function at any point right here. So this is the definition we're applying right here. Okay, so number 10 is about doing that. Okay, and of course you're told to use it, to apply that definition. So let's do it. Okay. F of x is 9 minus h, right? And f of x plus h, so this is x plus h, x replaced by x plus h, so x is replaced by x plus h, right? And we're going to work on the definition. So it's an algebraic process combined with limit finding. Plug in, right? F of x plus h. Substitution here. I'm sorry, this is it's going to be pushing 2 hours. Okay. And then naturally we would do conjugates. We do conjugates, right? We cannot take the individual limit. Numerator approaching 0, denominator approaching 0. We cannot use the limit law either. And here, if you wish, you can write 9 minus x minus h, but I just keep it the way it is. Okay, the conjugates. The conjugates, so of course, this is going to be turning into plus. Principle number 1. Okay, so the conjugates equals to the numerator times the numerator, denominator times denominator. So the denominator is going to multiply the denominator and the numerator times the numerator. Numerator times the numerator, so we're going to get the square, right? We know that a, I'm going to quote you the formula. Okay, so a minus b times A plus B equals to, you can see how useful that formula is, right? There's just always useful. Okay, so next, right? So we're applying that, we are basically applying the root of omega instead of using x, right? That piece squared is equals to omega. We talk about this in class many times over, right? So omega squared, these two are different, right? Be reminded they're not the same because the expression on the left-hand side have different domains. All right, so we're applying the first one on this piece and on this piece individually. And on this piece, and we'll be left with 9 minus x plus h. And on this piece, it's just 9 minus x, right? So this piece is just going to be like that. Open up the parentheses. Open up the parentheses, right? Minus x minus h, right? So you could have opened it earlier, but it doesn't matter. Minus x minus 9 plus x. Okay, there's some of these, tiny little details that you don't want to make mistakes. 9 minus 9 makes 0, positive x, negative x. So we have a negative h left. And the h on top and h in the bottom, they're not 0 because h approaching 0, but h cannot be 0, right? Limit definition. So these two h's are gone. One from the top and one from the bottom. Then the parentheses in the bottom is no longer needed. By this time, finally, we can do direct substitution. Okay, the consequence of the direct substitution is the following. H will be replaced by 0, no other h, right? So in the end, and 0 is gone, right? So we have 2 of the square root of 9 minus x under negative 1. That's the answer. So in the end, and of course we have finished, I hope it's under 2 hours. So that's the answer. Okay. Thank you for watching. If you have any questions, please don't hesitate to reach out to me and I'll be happy to answer your questions. Thank you for watching.